So I'm Nadine Meyer and I work on levitation optomechanics. And in comparison to all the experimental platforms that we've seen during this week, this will be a little bit of change of topic, but I hope that there will be lots of beautiful pictures. So just lean back and enjoy the ride. There will be lots of photons, and will also be lots of atoms in the form of a nanoparticle, but everything will be a classical experiment. Yeah, so bear with me. So I want to talk to you about accelerated state expansion of a nanoparticle in a dark inverted potential. And I try to mimic here the essence of the experiment, where we take optical fields and electrical fields exposed by electrodes around the particle to create such a delocalized state of a nanoparticle. And because I would like to concentrate on one specific experiment, I don't have time to talk about all the other activities that we have in the group. So on one big aspect is that we would like to miniaturize our optomechanical platforms, both the electrical interface and the optical interface, and this can be fiber-based or based on metasurfaces. We also have an interest in cavity optomechanics, where we would like to couple the nanoparticle motion to the cavity field and study the motion in the strong coupling regime. And we would also like to engineer the forces that our dielectric particles and membranes see. And for this, we exploit high reflective index materials and the Meyer resonances that appear in these kind of systems. And we do this with clamped systems, and we would also like to exploit this further in the future for levitated particles. And then we also study our oscillators in the classical regime, where we here now have stabilized the unstable branch in a bistable oscillator. And last but not least, it just came out today on the archive, we also apply now coherent feedback to our levitated nanoparticles to cool its center of mass motion. So we would like to use levitated nanoparticles as optomechanical system, and the experimental platform all goes back to an idea from Arthur Ashkin when he invented the optical tweezers. And as most of the optomechanical platforms, we can use them to test the limits of quantum mechanics, and we can also use them for sensing. But specifically for levitated nanoparticles, you're dealing with a steady state that is not equilibrated with the environment. So you can also think about exploiting this for non-equilibrium physics. And you can also think about studying material science under extreme conditions, because this is a highly isolated single nanoparticle in a controlled environment. And these single nanoparticles have a very high surface to volume ratio, which is a fairly uncommon condition in material science. So back to optomechanics, nanoparticles, as all the other optomechanical platforms, can translate, but we also have other degrees of freedom that we can exploit and study, like, for example, rotations. And most importantly, we can dynamically engineer the potentials, meaning we can also switch off the potentials and let the particle evolve freely. As we've mainly dealt with atoms and two-level systems this week, I want to highlight a few aspects about our platforms. Nanoparticles are not atoms, so they are not indistinguishable. So if you ever want to build up quantum statistics, you need to make sure that you use the same nanoparticle over and over again. We have no internal transitions to cool, for example, with laser cooling, so we need to come up with other ways to cool the center of mass motion. And but on the other hand, we have no need for nanofabrication, because these particles are actually commercially available. Because we are levitating these particles in vacuum, we have no clamping losses, and they are very well isolated from the environment, meaning that we have a high Q oscillator at room temperature. So there's no need for cryogenics at the moment. Typical parameters that we work with is that we take a nanoparticle of silica. This is our material of choice due to the low absorption in the near infrared. Radii range from 50 to 200 nanometers, which means that we are dealing with like a billion atoms. And this sums up to a mass of 10 to the minus 18 kilograms. The typical mechanical eigenfrequencies in our optical traps is around 100 kilohertz, and this is mainly given by the density of the particle. Bringing this all together, if you want to think about quantum experiments, they happen at the length scale of the 0-point fluctuations of the ground state. And this is dependent on the mass and the mechanical eigenfrequencies, and this sums up to a picometer scale. So this is a small length scale, but hopefully not something that hinders quantum mechanical experiments in the future with these kind of systems. So we have an optical potential most of the times where we levitate a silicon nanoparticle in front of a high NA optics. In this case, this is a microscope objective. And then if you look at the motion of this nanoparticle in frequency space, you can see that you have three very well isolated and nice center of mass eigenmodes in the range of 40 to 200 kilohertz. And the trap stiffness of these optical traps is now given by the particle polarizability, the intensity you use, and how well you can focus your beam. So a typical experiment can look like this, that you take a near-infrared laser, you send it through a microscope objective to focus the light, you trap a particle at the focus, and then the particle scatters the light, which you can collect with collection optics, both in the forward and in the backwards direction. And due to the fact that most of our particles carry a surface charge, we can also put electrodes around it that exert electrical forces on the particle. And if we use plasma, we can also actually control the charge of the particle down to a single elementary charge on a nanometer sized particle. And if you now look at, so now a particle oscillates at room temperature, and if you translate this into a phonon occupation for a 100 kilohertz oscillator, then you end up with a phonon occupation of 10 to the 7. So you would like now to go towards ground state, meaning that you need to scale this down by 7 orders of magnitude. And this has been the main activity of the community in the last decade and has been achieved now both in along one center for one mode and two modes, but also with different methods like active measurement-based feedback or using a cavity and performing coherent scattering. So now that we are in the ground state and knocking at the door of quantum mechanics, we would like to create a macroscopic quantum superposition of large masses. And this is a collaboration between the group of Oriol Romero-Isard at ICFO, previously at Innsbruck, and Markus Asmelmeier in Vienna and Lukas Nowotny at ETH Zurich. And the idea behind this experiment is the following, that you start off with a nanoparticle with a very high purity state, meaning that the wave function is very well localized, much, much smaller than the nanoparticle size. And we would like to expand this wave function of the particle to sizes much, much larger than the comparable to the nanoparticle size. So if you're thinking now about the actual dimensions, then here you are picometer size, and here you would like to be hundreds of nanometers large. You need to bridge at least like 5 orders of magnitude in the expansion ratio. So to do so, we need to start off with a pure state and low phonon occupation. This has been achieved in the community in the last years. And now we would like to create this large expansion and delocalize the particle. And then we would like to prove that we created this macroscopic quantum position using nonlinearity in our case, in the potential. And we need to do this, obviously, in an environment where we have low decoherences and fast dynamics, such that the decoherences don't decohere our state. So the figure of merit in our experiment will be the coherence length, which is basically a product of the purity of the state and the state size. And here, just schematically, I tried to sketch where we are at the moment. So here on the y-axis is the purity. Here I have the state size. And the ground state lives in this upper corner here with a high purity, but very small length scales for the state size. And this has been in an optical experiment been increased past the coherence length of the ground state with a high purity state. You can also approach it from the other side by starting off already with a low purity state, but that's much larger, and then expand it even further. And we would like to push it further up this corner where we would like to be for a high coherence length. So the protocol that we would like to use has been discussed already by Piotr on Wednesday. So I will only flush it here now. You start off with a particle sitting in a double well, and we only want to use 1/2 of the double well potential because it has a few key ingredients. First of all, it has this inverted part here that we would like to use for coherent state acceleration, accelerated expansion, sorry. And then we would like to use the quartic potential to create the Wigner negativities in the phase space, and then we recatch the particle to read out. And here I will only talk about this step of the protocol, so the dynamics in the inverted potential to create this larger state. And again, is only classical dynamics. Yeah, so we are still dealing with a thermal state of higher phonon occupations. The platform itself looks like this, where we now have an optical trap that catches the particle, and around it we have a chip that accommodates a certain set of electrodes, and there are basically 3 tasks that this chip needs to do. So on one hand, it needs to provide a Paul trap, which is these 4 electrodes here. Maybe you can see them better in this picture here, which are now 45-degree rotated in comparison to the optical axis of our detection, basically. The second one is that we have feedback electrodes around it to exert electrical potentials and homogeneous forces such that we can cool the center of mass motion. And most importantly, due to the fact that we stacked these Paul trap layers, we can engineer the potential the particle is seeing along the optical axis by applying a different DC voltage on the Paul trap electrodes. And if you want to create a double well, you would basically alternate the voltages in a certain way, where red is now positive and blue is negative. And we can actually map out this double well experimentally by moving the particle along this double well, and then at each position we measure at the amplitude response if we drive the particle in this double well. And given the amplitude of the motion, we can then translate it into the potential the particle is feeling. And here you can see that now a double well that we have in our experiment, it is a little bit skewed due to the fabrication of the chip, but not a problem for us at the moment. And also, we don't care that much about the symmetry because we only want to live in one of the double wells anyway. So we create an inverted potential frequency of around 1.4 kilohertz for a particle that is charged now with 84 charges, and the size is roughly 200 micrometers. So for our experiment here today, this doesn't really matter how large this double well is. In the future, this will need to shrink down quite significantly because you need the particle to explore also the entire part of the potential. Therefore, 200 micrometers is very big. So to initialize the state, we do 3D cold damping with electrical forces, and to do so, we collect the scattered light on a detector and then feed it back, applied with the gain on the electrodes in the experiment. In this case, they are distributed along the optical detection axis. And then this is now then a position dependent force. Yeah, for cooling, you don't want this. You want actually a velocity dependent force. And we create a velocity dependent force by just applying a delay by a quarter of a period, because we have a harmonic oscillator, position and velocity are linked. And this allows us then to cool down the nanoparticle to around 10 phonon occupation along the optical axis. This is the best cooled direction because we have the best detection efficiency along this direction. So, and this means that we start now with a state size of a few tens of picometer. So to summarize what I've just said, this is now the experimental protocol. We start off with a particle in an optical trap. It's sitting in this hole of this chip. We put a Paul trap around it, which creates an overlaying harmonic potential on top of the harmonic potential of the optical trap. The particle is moving by the thermal motion. We detect the motion and then we apply the cooling force, and we can do this in 3D and therefore cool the particle to the 10 phonons along the optical axis. And then we can superimpose our double well along the optical axis and let the particle evolve in this dark potential. So because we only care about the dynamics at the moment for the inverted potential, we simplify the experimental case and actually only apply the inverted part by changing the electrode configuration down here, and then let the particle expand in this potential. So just the experimental sequence is then looks like the following, where you have basically the optical trap, we switch it off, we let it expand, and then we measure, and then we stabilize the particle again. Just a side note, the Paul trap and the inverted potential say always on, but this is not a problem for the state initialization because the optical trap overpowers the Paul trap. And the frequencies between the optical trap, which are in the range of tens or hundreds of kilohertz, compare now to the Paul trap frequencies that are around a few kilohertz. So in our measurement, we retrap the particle in the optical potential, and then we see it oscillating at a larger amplitude. And we are interested in the state the particle has at this point. And if we just look at the kind of the summed up time trace, we will not get this information. So we kind of need to retrodict in a lock-in operation the information that we get from the measurement to the point time equals 0. And therefore, then we can tell you what the position and the velocity was at this case. So we do this 400 times and then map out the phase space. And as you may, now I want to dig deeper down into the experimental results. So if you may remember, I'm doing a 3D expansion experiment. So I have in the Paul trap plane, I'm doing a frequency jump protocol where I basically release the particle from a stiff optical trap into a shallow electrical trap. And then I let the particle expand and I retrap it and I read out the amplitude. Along the optical axis, I have and I can describe the variance of the state with the following equation. This here is a heating term that I would like you to forget about now, and I want you to pay attention to the expression in the bracket. So here you have this. It's first of all, it's rotating in phase space, and then the largest expansion is given by this prefactor here. So it's bound by the ratio of the two frequencies. So in the best case scenario, you would make this as shallow as possible, and then you have free expansion, basically. Along the inverted potential, the particle is following the inverted potential, is also being retrapped. And now if we look at the expression for the variance here, it looks at first very, very similar, but there's a very important difference that the trigonometric functions here are replaced with the hyperbolic expressions. And if you now, just for simplicity, assume equal frequencies, you can maybe see that this is an exponential. So you get an exponential increase of the state size with time. And it's also not bound. Yeah, so there's no limit to it. So now going to the experiment in the Paul trap plane where we do the frequency jump protocol, we let the particle evolve for tens of microseconds, and then we map out the phase space distribution. So here is a histogram of the position distribution, and we get a standard deviation of the state of around tens of nanometer, and increases if you let it go even further. But then because we are in this frequency jump protocol and the phase space is rotating, you actually get that the state is shrinking at larger times again. And if you plot the standard deviation over time, then you get exactly this oscillatory behavior, where you have the largest expansion at a quarter of the period of the lower frequency, and the recompression at half the period. And on top, you have like these micro motion wiggles that come from the Paul trap itself. This is well known. And here, as comparison, I plotted the free expansion, which follows for short times the very same dynamics, but then it would actually overtake the frequency jump protocol as soon as the expansion here is turning back and shrinks again. And we can do this in the two different Paul trap axes, and in both cases we recover this oscillatory behavior. This maximum state size is around 20 nanometers in both cases. Good. And relative expansion ratio in this case is around 60, and this is also due to the fact that our state in this direction, the initial state, was much larger than, for example, along the optical axis that I discussed with you before. So now actually our axis of interest along the optical axis, where we have the inverted potential. So after 80 microseconds, our state is still only a few nanometers in comparison to the other one. This is much smaller, but this is already due to the fact that this state initially was much, much smaller. So this was tens of picometers in the beginning. And if we now let the particle evolve even further, the state grows and it actually keeps growing. So it never shrinks again as we expected. And we can now plot the standard deviation over time, and we can see that the growth is actually following an exponential curve that reaches the maximum standard deviation of around 40 nanometers. So if you now think about the initial state size, this is a relative state expansion of nearly 1,000 now. And in comparison to the inverted potential dynamics, I also plotted here the free expansion. And now, most importantly, our exponential growth here is overtaking the free expansion, and we are gaining actually in expansion. And here's just a little zoom in into this region up here. So we are gaining at the moment a factor of 2. We are mainly limited by our detection limit not being linear beyond this, so we can also have data points further up here. The curve is just harder for us to interpret the data yet. So great, a factor of 1,000 in expansion, but the expansion actually doesn't come just from the coherent dynamics, it's actually also heating. So we have quite significant decoherences and heating effects in the system because it's not optimized for this. Due to the fact that we are working in the dark and we switch off our optical potential, this is already good because we don't have photon recoil heating, but we will still have gas damping. And we will also have electrical noise, and in our case at the moment it's still the electrical noise from the electronic equipment and not, for example, anomalous surface noise heating as observed in ion traps. So as a heating rate, we still recover tens of kelvins per second as heating rates, and this means during the protocol times that we are doing this, you lose any kind of purity during this time. So there is a subtle difference due to the fact that we're using an NRF potential in the Paul trap plane and a DC potential in the along the optical axis for the inverted, meaning that in the Paul trap plane the gas collisions are not dominant. It's actually our electrical noise, and along the inverted potential the two factors are actually comparable. And now, in the interest of time, I will skip the last part. I just want to highlight that if you believe that I can describe the data with my model, I can actually describe all variance and covariances in the same way because they depend on the same parameters in the same way, and I could actually extract the purity out of this position measurement. And therefore also estimate the coherence length. And with this, I skip this. So I hope I convinced you that we created this large state of tens of nanometers with nearly 1,000-fold increase in state size. We have the community now has this low photon occupation state. We add a method for large expansion to it, and now we need to bring everything together for the double well protocol. We need to work on the decoherences and actually a better state estimation, because the smaller you go with your state, the harder it gets. We would like to introduce the nonlinear dynamics, which we already have in our system. And in the future, we actually need to work on the double well potentials. And with this, I would like to acknowledge the people who are actually doing the experiments. So there's Grégoire Tomassi and Daniel Verhuizen, who are a leading role in this experiment, and also Bruno Melo, who has contributed to this work. And obviously, this all happens in the consortium of the Q Extreme, where I really want to highlight our theory support. And with this, I would like to thank you for your attention.
Thank you, Nadine. Now we have time for questions, comments. Are there any? Yes, please. Just.
Florence, you go first.
Yes, thank you for your very nice talk. I was wondering, how good is your vacuum?
10 to minus 7. 10 to
Okay.
minus 7. So,
And
the problem with the vacuum is that our loading mechanism for the nanoparticles is really really bad. We open the vacuum chambers on a daily basis and then pump down. So, depending on how fast we are, we work in the range of 10 to minus 6 or 10 to minus 7.
okay, thank you. And would you consider using cryostat, or is it just like not a common practice?
So there is, for example, the group of Lucas Novotny, the experiment where they used a high purity state and increased the coherence length. This was done in a cryostat. So it is possible, and it might be also needed in the future because of blackbody radiation in general, to do the quantum version of this experiment, just to kind of test the different protocols. At the moment, it's not needed yet.
Makes sense. Thank you very much.
Okay. We have question over there.
Thank you. Thank you for the talk. And you mentioned at the end, no, that you can reconstruct the purity, or no, you have at least more or less depends on the same parameter. And in that case, during the expansion, what happens to the purity of your state?
It looks very bad still.
Is it worsen or not?
So it's this graph here. So basically, I'm plotting here now the coherence length over time during the protocol. This is the frequency jump protocol, and this here is the inverted potential. And I think you're mostly interested in the inverted potential, where in our case, the decoherences are so fast that we basically use all the coherence that we initially had. So there's not even a little bit of increase, as for example we can see in the case of the frequency jump protocol. But this is mainly due to but if we now imagine a case where we can improve our decoherence rate by a factor of 1,000, which will be first better vacuum, better electronic equipment, filtering, also thinking about trap shaking and so on. And then you enter actually the regime where you get this increase. And at this point now, it's foreseen that the delocalization is compensating the decoherences. If you can play this game even further, and then at some point this will just increase with time. But it's then a measure of how much you can actually decrease this decoherence rate as such.
Thank you.
Other questions? Yes, we have questions.
Thank you for the nice talk. I wanted to ask you about that expansion. You said that you were not able to measure past a certain point, and I thought the data looked interesting. You
So
had like
for larger.
yeah, the previous slide before that one, I think. Yeah, and I was
So you mean
curious.
do you mean the
Yes.
comment that I did that we cannot measure? So
Yeah.
we can retrap the particle because this is basically given by the optical trapping volume, which is hundreds of nanometers or maybe a micrometer. The problem is we are using a homodyne detection to read out the state, and this is then leaving the. So this is a sine wave, basically versus position, and all these data points here are still in the linear range of this homodyne detection. And the further you go this way, you start to have nonlinear effects in the detection. And at the moment, we are working on it, but we don't really are super confident about what we are seeing there.
Thank you.
Okay, I think that we should move on to the next speaker. Thank you, Nadine.
Thank you.